Thank you. Doing well? Yeah. Okay. Well, why does an iOS developer need functional programming? Well, there are obvious places. Sequences, async sequences, optionals, combine, and of course, SwiftUI. You think SwiftUI is like the gooeyest place, and yet functional programming is actually a big part of it. We just don't know it, we don't feel it, because it would just scare us away. Now, it's not pure, it's not perfect, but neither am I. I look at it as SwiftUI puts the fun into functional. And if you squint, you can see the container views are the same thing as combinators. I'm not going to tell you what combinators are. So, in this talk, what I want to do is I want to faithfully implement a paper that goes back 40 years, and it uses SwiftUI not 40 years ago, but in this implementation. So in 1982, how many of you were born in 1982? I thought not. You know we had computers then? Peter Henderson published a very famous paper on functional geometry. He revised the paper and he reissued it in 2002 using a different language. And mostly we're going to refer to the 2002 paper, but everything here goes back over 40 years. And in it, he drew a fish. He was inspired by an Escher piece of art, and that's what he was trying to achieve. And so he created this thing called combinators, and I told you I'm not going to explain combinators, but you can think of it as this geometry language. He had these primitives and things that you could build up from those primitives. And so he would draw fish, and they'd draw a second fish that had been rotated by 180 degrees and present them one over the other. And the code for doing it was this, which is readable, it's stunning. It's not SwiftUI, but it will be. In the 1982 paper, he used Lisp, and so he didn't use commas. They re-implemented it in Java, so in the 2002 paper, he did have commas there. We could write the same code in Swift exactly using that syntax, but that wouldn't be Swifty, and that matters to us. And so we can translate this into SwiftUI and write something like this. And at this point, I should hear, ooh. And so when you draw a fish and you rotate it, we want to get something that looks like that. And the fish were combined in many ways in his paper. Here's 4 fish together. Here's 3 fish together. And his North Star, what he was aiming for, was to implement in a computer an Escher print. And so this was his goal, and this is our goal today. Okay, and so that's Escher's square limit. So let's begin with a circle and end with a fish. So with circles, with SwiftUI, there's lots of ways to think of circles. In SwiftUI, we have a circle, and so we have a content view, and it's a body, and we can just say, well, a body returns a single view, and in this case, let's return a circle. And we get something that looks like this. And if you look at the docs, yes, for this there are docs. The docs for circles, it's a circle centered on the frame of the view containing it. And the way SwiftUI works, of course, is the containing view says to the baby view, hey, here's how much space I can give you. And the baby view says, well, here's how much space I need. And there's a negotiation. And so if instead we have an H stack, which is a container view, with 1 circle in it, we get the exact same picture. With 2 circles in it, we get this picture because we negotiate and it says, well, I need this much space, and to each circle, they use half of that space. And we get this, and if you go further and say, well, actually, I have an H stack, but no spacing, please, you might have noticed the circles got a little bit bigger because that space between them is now available for each circle. And so this H stack is a view that arranges its subviews in a horizontal line, and none of this shocks any of you because you're SwiftUI experts. An H stack has these parameters that allows you to specify vertical alignment, but by default it's centered, and that's usually what we want, the spacing. And then finally, and this is the magical piece, this view builder, which is a function. And because it's a function, I mean, you've done this so long you probably don't think about it. That's why it goes in curly braces, because we pull it out as a trailing closure. And the view builder is what keeps us from having to have the commas between the circles. And so this is what allows us to have this really nice syntax. And so in SwiftUI, our container views I think of as using this functional programming, and I'll come back to this notion later. And so that's sort of our notion of a circle in SwiftUI. Doing okay? Yeah. What about Swift? What sort of a language is Swift? Well, how many of you were around 10 years ago as programmers? So Swift replaced Objective-C for us on this platform. And so a lot of people came to Swift thinking of it as an object-oriented language. And that's how they viewed it. But at the time, despite the awful syntax, blocks were very popular in Objective-C. Closures, lambdas, and other languages, but these were blocks, and they'd started to catch on, and Swift was very friendly to closures. Like the syntax for closures in Swift, you went, oh, this is what I've been waiting for all my life. So maybe Swift is a functional language. But the FP stuff felt like it was way over here in the corner. Sure, we saw it in closures and map and filter and flat map, but flat map and array, there were actually 2 flat maps in array, and one wasn't even a flat map. And it took them years to rename it. So Swift wasn't functional, it wasn't OO, it was a sort of hybrid. So what's a circle in Swift? So I asked this online last week, and most people in my timeline answered me something like that. They said a circle is a struct that has a radius. And some people told me that it should also have a center, and that's fine. But essentially, this is what they told me. And you think, well, what do I want to do with a circle? The 2 things that come to mind are I might want to draw it, and I might want to determine is a point in the circle or not. And it's this second problem that let's start with. And so let's have an extension to circle. Oh my gosh, I love extensions. This extension will conform to a protocol that I'll call shape. And every shape knows how to determine if a shape contains a point. And so I say, well, do you contain this point? And in the case of a circle, it's just x squared plus y squared is less than the radius squared. And then that point is true. It's inside the circle. At this point, if you come from the world of functional programming, you're losing your mind. Because in your mind, that's the shape. For a functional programmer, a shape is a function. It's a function that takes a point and returns, is this thing inside the shape or not? That's it. What are you messing with structs for? Well, how do I create a circle? A circle has to return a shape, and so a circle is a function. I mean, that's why they call them functional programmers. So a function that says, you tell me the radius, and I'll return a shape, I'll return a function that tells you whether a point is in this shape, and now I return a function that accepts a point, that's that closure, and it's that same implementation that I saw before. And so this is what a functional programmer would call a circle. You say, well, I can check if a point's inside a circle. That's pretty easy. And I can start combining these things, and I can have, say, an annulus where I'm only interested in the things outside of this inner circle, but inside of the outer circle. Or I could take a byte out of the circle, and it turns out this is pretty easy to calculate. Doing this as OO is hard. In fact, there was a competition where they had to do something like this back in the 90s to determine what areas were safe and what areas weren't safe. There's a very famous paper by Hudak and Jones which compared a bunch of languages used for this implementation in the contest. The Haskell implementation used 1/10 of the code of the next language and was done in just a fraction of the time. This worried the sponsors of the contest so much that they taught a grad student Haskell for a week and had them attack the problem, and they were the second place winner. You might have seen this in a great talk by John Hughes, Why Functional Programming Matters, Or if you ever got the book Functional Swift by the OBCIO guys, this is the first example that they refer to in that book. It's a very famous example that goes back to the 90s. And the idea is that once your shapes are functions, it's very easy to combine them. And so I know what it means to be inside the unit circle. What does it mean to be not in the unit circle? To be not in the unit circle means I am outside of a circle with radius 1. And so I need that outside function, and it takes a shape, which is a function from point to bool, and it returns a shape, which is a function from point to bool. You guys still with me? So it just says, well, if you're in, then I'm going to return false, and if you're out, I'm going to return true. It's just the not shape of the point. It's trivial. And so if I want to calculate this annulus, I need an intersection of all the things that are inside the big circle and outside of the small circle. An intersection is just implemented as taking two shapes and returning another shape by saying you're in the first shape and you're in the second shape. You are both in the circle of radius 4 and you are outside the circle of radius 1. I wish it was harder. Oh, what do you mean you want to draw a shape? Oh. In OO, shape would be that protocol, and every shape would know how to draw itself, and that's really hard. SwiftUI, since we've got these functions that return true or false, we can use metal shaders, and we can color it in if it returns true, and not color it in if it returns false. Metal shaders evaluate all the points, and they use the graphics, and they work very fast. They evaluate each point in some method. And so, for example, I have this draw. Now, it looks very C-like. That's the drawback. But somehow I figure out if I'm in that annulus, then I'll color it one way. Otherwise, I'll color it another way. Very easy to work with a shape that has told you is it true or false based on the point. I've skipped the part where I re-implement the circle in metal because that's not the point, but you can draw shapes. And the way we would do this in SwiftUI, because SwiftUI can now use metal easily, is I take a rectangle and I say, hey, rectangle, apply the color effect that draws the shape, and I get my annulus there. Oh. Thank you. No fish yet. Now, I've separated the shape from the code that draws the shape, and that's a big step. A shape is a function. I have this way of producing shapes like a circle, and I have a way of combining shapes. And that's this sort of geometry language. That's this idea of these fundamental shapes that get combined. And that solution is from 1994, and it's related to this exploration from that Peter Henderson paper from the 1980s, and that's where he developed his picture language, or what we call functional geometry. And so that was an ACM paper in 1982 that he revised and updated 20 years later, which is still a long time ago, before Swift was born, before the iPhone was born. Really. You may also know this from the structure and interpretation of computer programs by Abelson and Sussman. It's in their book, and it's also in the videos from their book, and that's where a lot of people know this example. John Hughes also mentions it in his functional programming talk that I mentioned earlier. And they start by saying, a painter is a function. You give me a frame, and I'll produce some output. It's a way of drawing shapes. And this is how they described a frame. The origin is somewhere, and then there's something that defines the bottom and something that defines the side. And it didn't even have to be rectangle. It could be a parallelogram. I'm going to restrict this to be a rectangle, just because. It doesn't have to be parallel to the axes, but it is a rectangle. And so a painter is a function, and what we just said is in Swift, I want it to take a CG rect and return a path. And so that's what I'm using for my painter. And so if you tell me where I'm supposed to paint inside of these lines, then I'm going to create a path. And so I have this thing that makes it easier. This is just a little helper thing for me so that I can say, move to x10, y10, and it's a tenth of the x direction and a tenth, so it's 10%. And so it makes it easy for me to move to a place, add a line across, add the rest of the F. And now if I want to display that inside SwiftUI, I say just show me the F, and I get the F like that. There is an invisible cheat that you can't see, and that is I've set at the level above this that it's drawing inside something that's of aspect ratio 10. So I'm restricting this to draw inside of a square. Otherwise, it would have stretched the F all the way to the top because it would fill all the space. So I'm going to work from now on inside this square. I'm not going to show it, but there'll be a square. And so this is this painter that goes from my rectangle, that bounding square, and gave me the F path. And it depends on the rect. So if I divide that rectangle in half and I draw an F on each side, I get something like this. I get a function from CG recta path on each side, and I combine them with this method that I'm going to call beside. And beside will draw one picture next to another picture. Oh, Daniel, isn't that an H-stack? Shh, no. Nothing like an H-stack. So beside is a function that takes two painters and gives me a painter. And so I need to return a painter, which depends on what frame I'm drawing it in. And so I scale one of the F's to only take up half of the space. And I scale the other F to only take up half of the space. And I draw them next to each other. And so when I do beside F and F, I get that. And that's implementing it in Swift. I'd like to implement it in SwiftUI. This was the first 4 pictures that Henderson said, well, let's implement this. And so the F, I'll use that same basic function, but I'll put it inside of something called F-curve. And this struct F-curve has a body. And the whole reason I do this, you SwiftUI people, is I need to know the size of the box that it sits in. And I use a geometry reader for that. And I pass in the frame to my F path. And so it says, oh, I'm drawing it in here. And when I do beside, it's drawing it in the narrower one. And so I'll stroke that picture, and then I'll get what I need. And so that gives me my F curve. And I've drawn an F. Now let's rotate it. Oh, no, rotate is taking a function. So I'll create a struct called rotate that's also a view. It needs to know the view that it's rotating. What type is that view? I don't know. And that's why we have generics. Anything that conforms to view, image, whatever it is, I can rotate, I can mess with any of these things. And so inside of my body, I just take my view and I rotate it by 90 degrees. If you're old enough to know timepieces that go clockwise or counterclockwise. And so I rotate my view F. I really want it to look like that, though. Oh. So I want it to somehow accept F in these curly braces, and I want to call it ROT. And so let's make 2 changes. Change 1 is I'll add an init. The init will take a function that returns my A, and so I'll just return it. And the other thing is I'll type alias rotate to ROT, and now I've got a rotation of F. There's more. I know, still no fish. The next thing is to flip in the horizontal direction. That looks exactly like rotate, except I'm scaling it, and scaling the x direction, -1, is what flips it in that direction. Another type alias, and now I can call it flip F. And oh my gosh, if you flip F and then you rotate it, woo, I got that for free. Nope, still no fish. Henderson gave us another series of things. He said, well, okay, now draw these. And these are the things that you do. You know when you go to the dentist to have your teeth cleaned, and the actual polishing is like the last 2 minutes? But for the first time, they're just poking and dragging and scraping. So we're doing the poking and drag and scrape stuff. The fish is going to be the polish at the end. So I have above F and F. I want to combine two views. Before I get to that, I want over. Over will draw one thing behind another so that I can see things that are superimposed on each other. The big thing is it's going to take two views this time, not one view. And so I need to store those two views. Once I've stored them, in this case, I'll just use a Z stack because that works for us already. And I'll use the type alias over. Calling it, though, is going to require another init. The init is something that returns a tuple of views, or depending on how you were raised, a tuple of views. And so it returns that. I'm going to call the thing that knows how to do this a to-builder. A to-builder is going to be the thing that makes this work. A to-builder is something that we call in Swift a result builder. And a result builder must have a method called build block, at least one. And in this case, my build block will take two views. They might be the same type, they might be different types. And I will have a view of type A, and I will have a view of type B, and I will default the second one to an empty view so that if I try to build and I just pass you one view, it'll draw it with the empty view as well. And it'll return A and B, and that's to-builder is what makes this work and what makes us able to call this with the curly braces. I want to draw an F over an F rotated. Not the prettiest picture you've ever seen, but the code is gorgeous. So once you can do this for two views, you can do an above, which takes two views, and the only difference is, in my above, I'm going to scale the top view by anchoring it at the top and scaling it to a half, and I'm going to take the second view and I'm going to anchor it at the bottom and scale it by a half, and now I show one above the other, and that gives me above FF. And the code isn't that hard, is it? But if you've ever read Swift docs, they emphasize the code you write, you decide whether it's good code or not by looking at it from the call site. And from the call site, I find this spectacular. We can draw two things beside each other the same way. We just do it to the leading edge and the trailing edge by a half. We type alias and we get that. And now we can start combining them and say, look, draw two things beside each other above a third thing. And so above beside FFF gives us that picture there. So we're building a language. A language has rules. And this is delightful. I start with something, and I rotate it, and I rotate it again, and I rotate it again, and I rotate it again, and I'm back where I started. And so one of our rules is you apply rotation 4 times, you should always get back to what you started. And that allows us to start reducing things. If we have something with 5 rotations in it, we can take out 4 of them because 4 in a row do nothing. Another rule is if I have F above another F and I rotate that whole thing, that's the same thing as if I have 2 Fs beside each other, but first I rotate each one of them. And there's a ton of rules like this, and that's what a language has. It's an algebra. So there's many others. Our next transformation is not going to have nice rules. So let's wait a minute. And I want to do something different to beside because we're going to need it later. For beside, I want to say something like this. And what this says is the ratio of the widths from the first F to the second F are 1 to 3. In other words, the first F takes up 1/4 of the width, and the second F takes up 3/4 of the width. And so instead of hard coding a half there, we have some sort of a scale, and we use that scale instead, and we calculate the scale by passing in the ratios 1 and 3, and do 1 over 1 plus 3, that's 1/4, and 3 over 1 plus 3, that's 3/4. And notice the default are 1, so if you don't put in any scale, it's a half. They're equal. And so that's how we get this picture, and this one still works. Our last one is rotation 45. And man, this one looks different. Do you see how it even leaves its world? It's not even in its box anymore. And so it is rotated at 45 degrees. It has scaled it by root 2 over 2, and sometimes it leaves its happy little world. So rotation 45, I've drawn the original F so you can see what it did. That's kind of cool. Now Henderson says, rotation 45 doesn't really belong here. It's only in this paper because I wanted to draw fish. So it's time for the fish. I'm sorry? We're out of time. I can't show you the fish. Okay, here's the base of the fish. Take that base of the fish. There's the vertical. And all of a sudden, I'm getting a little excited because I kind of see a little fish there, but I'm also seeing symmetries. I'm going to see how one fish can slide in and fit next to another. Now, for this diagonal, I take that side, and I'm going to flip it over in sort of a 45. I'm going to shrink it down. And now I'm going to flip this. And so that side consists of two of these rotation 45 ones. And there's the fish outline. And it kind of fits in this triangle. The same things are added and subtracted. And you can think of tiling a plane in triangles. So you can think of tiling a plane in fish. And of course, So there's my fish. Let's have some fun. If I have a fish and I rotate it 180 degrees, ooh. If I have a fish and I shrink it and rotate it, and you know when your code calls you and says, oh, you need to do this next? Like there's a little tiny fish shape at the top, just calling for you to put your other fish there. And so this is 3 fish together. Oh, get rid of the big fish. And do you hear your code calling to you again? It's saying, rotate me. And now you get 4 fish. And these are our building blocks. So I need something called a quartet. A quartet of a circle, a rectangle, an F, and a fish draws the circle beside the rectangle, the F beside the fish, and that first beside above the second beside. And so it arranges them that way. There's a variant of this called cycle, which you give me one shape and it draws a quartet out of them, but it rotates them in each one. And so here's a cycle of F. And that we'll use as well. And so it's these, remember, these fundamental shapes and these ways of combining shapes. And so I'll use a quartet starting with these. I'll do 4 of these and I get this. And now it's starting to look interesting. I use a cycle starting with this 3 fish, and I get this. Now, we're going to draw the rest of the picture. And one thing you'll notice is I'm going to add 4 sides here, but notice that they're different. That's why I needed the beside that took 2 values and the above that took 2 values so that I could have them sort of shrink as they went up. And so I have 4 sides, I have 4 corners, and I put them together using this thing that uses the above 1, 2, and there's all my views, A, B, C, D, E. I repeated E here so you could see that's the center one. E, F, G, H, and I. And so there's my 3 rows, and this is called a nonet, 9. So here's my side. My side is a quartet. My quartet starts with the rotation of 3 fish and 3 fish at the bottom and 2 empty views. We will always, on all sides, have the same bottom for our quartet. And we're going to iterate. And so this side 1 will be the top left corner, and this side 1 will be the top right corner when we go to side 2, and now they start shrinking. And now we iterate again, and side 2 will now replace us. This is side 2, and so now we're starting to fill this guy out. Isn't that the coolest? Yes, it is, Daniel. Show us more. Here's corner. Corner has 3 empty views and 4 fish. I will always have 4 fish in the bottom right, and I'm going to start filling it out as I go up and over. And so side 1 and the rotation of side 1, and then corner 1 fills out there. And now I iterate again, keeping 4 fish in the bottom right. and I get this, and now it's time to put them all together. And so in my nonette, I have my center of the 4 fish, I have my side that I've rotated and put in each of those spots, and I have my corners that I've rotated appropriately and put in those spots. And so I have my center with the side, I rotate it, I rotate it, I rotate it. I have my corner, I rotate it, I rotate it, I rotate it. And so with SwiftUI and functional geometry, there are your fish.